Let us now look at application of integration in kinematics. Now, in differentiation, we observed the following: that the gradient function ds over dt is equal to velocity v, and dv over dt is equal to the acceleration a. It follows, therefore, that ds is equal to v dt. So that integrating both sides, we find s is equal to vt. That is, displacement is equal to velocity times time. Similarly, for the second case, with dv over dt is equal to a, then dv is equal to a dt. Integrating both sides of the equation, we get dv is equal to a dt, so that v is equal to at. That is, velocity is equal to acceleration times time. So what we find here, therefore, is that integrating a derivative function where displacement is differentiated with respect to time gives us the velocity, gives us the displacement. S, which we have found will be equal to v dt. And again, a derivative function, integrating a derivative function where velocity was differentiated with respect to time gives velocity which is equal to a integration with respect to time. So this is equal to vt, and this one is equal to at respectively. So we want to look at an example that applies the knowledge we have learned about. Find the displacement of the particle moved in the time interval stated in each case. So we have v is equal to t squared plus 2t plus 4 from t equals to 0 to t equals to 5. So because we want displacement, we have to write v in terms of displacement and time, so that ds over dt is equal to t squared plus 2t plus 4. ds will therefore be equal to t squared plus 2t plus 4 dt. Integrating both sides, 2t plus 4 dt, so that s will be equal to t cubed over 3 plus t squared plus 4t. And because we have been given the range, this becomes a definite integral, 0 to 5, in the range 0 to 5. This is equal to 125 over 3 plus 25 plus 20. So that s will be 41.67 plus 45, which is equal to 86.67. Whatever units will be the displacement that is required. In the second case, we have ds over dt is equal to t squared plus 2, so that ds is t squared plus 2 dt. The displacement ds will be equal to integration of t squared plus 2 dt between t is equal to 1 and t is equal to 3. S will be equal to t cubed over 3 plus 2t, 1. This is equal to 3 cubed over 3 plus 6 minus a third plus 2. This is equal to 15 minus 2/3. This is 12.67 assuming velocity is in meters per second, we can let time to be in seconds, so displacement will therefore be in meters in each case. In example 2, we want to apply the second case where we found that dv over dt is equal to a. So the question is, find the velocity v and calculate its value at the stated time, given that at t is equal to 0, v is equal to 0. So these are the initial conditions that we are given. In the first case, dv over dt will be equal to 9t squared minus 6t. The brackets have been removed. This becomes dv is equal to 9t squared minus 6t dt. When we integrate both sides, we get dv is equal to the integration 9t squared minus 6t dt. V is equal to 3t cubed minus 3t squared plus a general constant c. But we are given that for initial condition t is equal to 0 when v is equal to 0, so that 0 is equal to c. So our constant, general constant, is equal to 0, and therefore the velocity therefore becomes v is equal to 3t cubed minus 3t squared plus 0. At t is equal to 3, v will be 3 into 3 cubed minus 3 into 3 squared, which is equal to 81 minus 27, so that our velocity that is required becomes 81 minus 27 is equal to 54. Let the units be in meters per second. In the second example, when we open the brackets, we get dv over dt, which is equal to a, is equal to t raised to power 5 plus 2t raised to power 4 minus t cubed dv is equal to t raised to power 5 plus 2t raised to power 4 minus t cubed dt. Integrating both sides, we get here v is equal to t raised to power 6 over 6 plus 2t raised to power 5 over 5 minus t raised to power 4 over 4 plus c, which is a general constant, but v is equal to 0 at t is equal to 0. Therefore, c is equal to 0. Our equation therefore remains v is equal to t raised to power 6 over 6 plus 2 over 5 t raised to power 5 minus t raised to power 4 over 4 substituting for the value of t equals to 1. We get therefore that v is equal to 1 over 6 plus 2 over 5 minus a quarter. Here the LCM will be 60. So this will be 10 plus 24 minus 15. This gives us v is equal to 34 minus 15, which is equal to 19 over 60. Giving us a value of 0, v is equal to 0.3167 meters per second.